Righto. Well, today I'm pleased to introduce today's session, Advanced RAG Optimization to Build and Ship Production Ready RAG. And our guest speaker, Aravind, is a data and product enthusiast with 15 years of experience in data analytics and product. He's currently co-founder at Crux.ai, makers of the open source tool RagBuilder at ragbuilder.io. He's worn multiple hats in his career: analyst, technology architect, data engineer, product manager, and was previously leading cross-functional teams at Colbert and at Meta, you may know it as Facebook. So welcome, Aravind, and take it away. Really looking forward to the presentation.
Thank you so much, Stefan, for the intro. Hey, everyone. Super excited to be here, to be talking to you about RAG optimization. How many people do we have in, Stefan? Just curious.
So it looks like we currently got 24 attendees.
Awesome. I think it's Thursday morning or probably evening or probably late night in some places. So really appreciate all of you folks dialing in. I think this is a topic that's super close to my heart, and really excited to go through some of the advanced RAG optimization techniques with you all. So before we get started, I think Stefan already introduced me, but really quickly, I'm Arvind. I'm co-founder at Crux.ai. We are building in the RAG optimization space. We are building in open source. So super excited to talk a little bit about that as well towards the end of the talk. But if any of you want to connect over LinkedIn, there's a QR code on the screen. Feel free to reach out. Happy to chat, right? Now, so today we're going to talk about advanced RAG optimization. Before we begin, though, I'd love to hear from some of you. What's been the biggest challenge when you have been trying to build RAG? I'm assuming a lot of you have tried building some sort of a RAG, either a POC or a prototype, right? And maybe some of you have also tried to create like production grade applications based on RAG, right? So I'm really curious to see what are some of the challenges that you all have faced. Data scale, accurate retrieval, chunking efficiently, yeah. Yeah, RAG pipeline flow. How do you design the RAG pipeline flow, right? Working with Fed-approved LLMs. Okay, interesting. Adding a layer of reasoning. Wow, that's super cool. Super interesting. Passing the correct contextual data. Yeah. So I think, as a lot of you already know, a RAG has a lot of moving parts, right? There are probably a few of you in there who are probably new to this topic of RAG. So I'll just take 30 seconds to give a quick primer about what a RAG is. So a RAG is a very interesting technique. It stands for Retrieval Augmented Generation. It's a technique that allows you to bring in external knowledge sources or data sources that you can connect to LLMs in a way wherein when a user query comes in, you don't have to rely on its training data, right? You can fetch context from the data source that you have connected, dynamically fetch the relevant context and put it in the prompt and answer the user question, right? So for example, assume you're a business, you want to create an AI chatbot on top of your website, which can answer customer queries about your products and your services, right? Now, you can't take off-the-shelf LLM. It's not going to be aware of your proprietary data, right? Your products and services, right? So it's not going to be able to answer any customer queries, right? So that's where RAG comes into play. All you do is take this knowledge base that you have, maybe a bunch of PDF documents or maybe a bunch of textual documents about your products and services, and you basically have this engineering pattern where you chunk those documents, you kind of embed them using some sort of an embedding model, store it in a vector database, and then when a user query comes in, you kind of dynamically retrieve the right pieces of context which are relevant to this query, put it in the prompt, and then send it to the LLM. And now the LLM would magically answer this question that the user has, right? So it's a super interesting technique. It opens up a lot of interesting use cases. I think it looks like a lot of you are already working with RAG. Would love to hear more about some of the use cases that you're working with, right? But overall, RAG has a lot of moving parts, right? As you can see, there's data ingestion, there's retrieval, there's re-ranking, there's generation, and so on and so forth, right? And so there's a lot of different failure points within a RAG, right? So the more components or more moving parts that you have in any engineering system, the more likelihood that it's not going to work, the more failure points you have, right? So typically in a RAG, given the number of moving parts, there are a lot of different failure points. So for example, the starting with the user question itself, the question may not be clear enough, right? Or it may be ambiguous, right? And so that may cause a failure. Or maybe, the data that you've ingested has not been stored in the most optimal format. I think some of you called out like ineffective or, inefficient chunking, right? That can affect the accuracy of the RAG, right? Similarly, the embedding model plays such an important role in the accuracy of the RAG, right? The embedding model that you're using may not have sufficient semantic expression ability. Maybe you're working in a very specific domain, and as a consequence of that, maybe your RAG is not performing well, right? Similarly, in the vector database, there are a bunch of different indexing techniques. I think this is, a Zillis event, so I assume all of you are familiar with Milvus, and it supports a lot of different indexing techniques. And so what's the right indexing technique to use, right, for your use case and for the kind of data that you're working with, right? Similarly, on the retrieval side, you might end up with low precision or low recall. And then finally, towards the generation, even if you manage to get the right context, you might not get the answer in the right format, or you might have incorrect specificity, or you might have an incorrect answer, right? So overall, there's a lot of different failure points of RAG. And a naive RAG gets you only so far, right? When I say a naive RAG, it's basically the very bare bones version of a RAG, wherein you just have this embedding, vector embeddings of all the data that you have stored, and then you're just doing a simple semantic search, simple semantic similarity search on top of that data, right? So that's the overall backdrop of why we're having this discussion, right? We want to look at what can you do to make your RAG production ready, make it reliable and robust enough where you can put in front of your customers, right? So that's a very broad topic. I'm going to spend maybe about a minute just giving you a broad strokes overview of what are the different techniques, at a high level. And what we're going to do is take a subset of some of those techniques, go into some bit of detail, look at some of those techniques in detail, and then if you have any questions around any specific technique, happy to take that offline. I'm happy to spend time with you, right? But overall, these techniques sit across 4 different buckets. So there's a bunch of techniques which come under pre-retrieval, right? Before you even look at retrieval, overall in the data ingestion phase, what are some of the things that you can do to improve RAG accuracy and performance? You can improve information density. You can, optimize chunking. You can, do a bunch of different transformations on your data so that retrieval, when you do retrieval, it's more effective, right? Now, retrieval itself, within retrieval itself, there is a bunch of different techniques. You can do query routing, recursive retrieval, fusion retrieval, and so on and so forth. A lot of you have also probably heard about graph RAG, right? So you combine graph RAG plus vector search, and so on and so forth, right? And then finally, in the post-retrieval, there's, after you retrieve, what are some of the techniques that you can, apply to improve the relevance and information density of the retrieved results even further, so that you get the best juice
or you get the best answer correctness out of the RAG, right? So there's obviously re-ranking. I think a lot of you might have heard about re-ranking. We'll look at some of the techniques there, and then there's a couple other things like contextual compression, corrective RAG, etc. Right? And then finally in the generation, there's a bunch of things there as well, where you can optimize top K chunks that are used in the prompt. There's prompt optimization, of course. A lot of you are familiar with DSPy probably, and there's like self-rag and a bunch of other things there, right? So let's look at a couple of techniques within each of these, and then what I want to spend time with you on is talk about how do you navigate this space, right? There's just so many techniques and so many moving parts of a RAG. How do you navigate this space? Given a data set, given a use case, what's the right approach to build a really good production grade, reliable, robust RAG that you can ship to production, right? Now, within pre-retrieval optimization, there's one very basic fundamental technique that I don't see a lot of teams using, right? So I want to talk really quickly about this. And basically, when you talk about RAG, typically you're working with a lot of unstructured data, right? And unstructured data is generally in a form where it's not optimized for a RAG setup. It's not optimized for search and retrieval, right? And it's basically, think of it like paragraphs and paragraphs of information. The factual density is very low, right? You might have one relevant fact, but it's spread across, 3 different paragraphs, right? So one very basic problem that arises when you take unstructured data in its original form is that you end up with a lot of chunks in the LLM context, even if you have a very efficient retrieval approach. And then that just increases the probability of an incorrect response, right? So the more chunks you have, the higher probability of incorrect response. And more importantly, you end up with a higher token usage and your cost is really high, right? So one very basic thing to do here is to improve the information density, where you kind of get rid of irrelevant information and noise. You kind of do information deduplication, right? So one interesting one interesting case study that I came across related to this specific approach is that of a financial institution that wanted to create like a customer-facing chatbot on top of their products and services, right? So this company had a lot of HTML pages that they were using as the data source, right? And so one very basic thing there to do is to programmatically remove all the CSS, HTML tags, right? So the first box that you see here, that's the raw HTML. The natural and obvious thing to do is to get rid of the HTML tags. But then even with that, the information density was low. So what these guys did is they used GPT-4 to do one level of data parsing where they sent this raw form of data through GPT-4 to improve the information density. So they used kind of a prompt saying, hey, you are helping build a knowledge base, for each paragraph, take that and condense it to the most factual and relevant information, right? So that's what this company ended up doing. And as you can see, while the accuracy went up, what was really interesting is the cost reduction, right? So they saw a 4x reduction in token cost because of this approach. So really interesting. One caveat here is that since you're using an LLM to do this information pre-processing, there's a risk of information loss, right? Because again, like the LLM may hallucinate. So it's recommended that you do this with a really powerful LLM, like a GPT-4 grade kind of LLM, right? So that's number one. Another technique that's relevant in the pre-retrieval optimization is query transformation, right? We humans are inherently very bad at asking questions, right? Like we typically suck at asking questions in the right way, right? And so often you'll have ambiguous queries or poorly worded queries, and a lot of times your RAG is facing customers who are probably not very technical, right? Like you probably end users are going to be like a layman person, right? And so for them, it's often going to be like ambiguous or poorly worded queries, or maybe like really complex queries, right? So how do you navigate that? what you again do is basically do some kind of query transformation where you take that overall, context or slight bit of history of the conversation along with the query that you have, and then you kind of use another LLM to reword it into a more relevant and more effective query, and then use that for retrieval, right? So hence pre-retrieval optimization, right? So in this particular example, as you can see, like a customer was having a conversation with this chatbot, and they were like talking about interest rates for the CDs, and then suddenly the conversation got to credit card, right? Like which credit card is good for travel, and now the customer is asking, tell me more about the interest rate for that, right? And now this query alone is going to be very bad at performing retrieval, right? Because there's interest rate in the query, but we don't know what product is the customer talking about, right? And so it's very important to do a kind of pre-processing here. So you would use some kind of a prompt here saying, hey, you're examining a conversation between a customer and a chatbot, and use construct a search query that will be used to retrieve the relevant documentation. And so what it would do is take this history of the conversation and convert it to a better query, right? So that's query transformation. But in case of complex queries, it makes sense to kind of break those down into subqueries and then, individually perform retrieval on those subqueries and then combine results. On that note, let's talk about ensemble retrieval or fusion retrieval, right? So in this technique, what you basically do is a lot of times one specific retrieval approach is not going to be sufficient to answer whatever question the user has, right, in the most effective way possible. And so what you want to do is leverage the power of multiple techniques. So as an example, in this diagram, we have a vector index, right, which is like dense retrieval method. So when a user query comes in, we're going to do a semantic similarity search on that, get the top K results, right? But maybe that alone is going to be insufficient, right? And maybe the user had, certain, abbreviations or acronyms in the query, or maybe they had some really important keywords, which are not semantically represented in a vector database. And so what you want to do is you want to combine the vector search with a keyword search, right, where you basically use some kind of a sparse retrieval method, right? Like BM25 is the most popular one, but basically what you do is you use the same query in parallel, you send it to this other retrieval which is going to do BM25 based keyword search, and then maybe you end up with a slightly different subset of results here. And then what you do is you combine the results, right? Now, how do you combine the results? You can use a technique called reciprocal random fusion. It's a very popular algorithm, nothing new. It's been around for a while, very popular in the information retrieval world. But essentially, you calculate like a weighted score where you combine the results from both retrievers and then send it to the LLM, right? So there's a case study here, which was, well, not a case study exactly, but like an experiment that was done by Microsoft. And basically, as you can see here, there's a comparison of keyword search versus vector search versus hybrid search. And the hybrid search clearly performed better, right? I mean, it's kind of obvious, right? Like we are combining the techniques of two different methods, right? And what's interesting in this case is they also had this fourth option where they took the hybrid retrieval, but also performed a re-ranker on top of that. And that was even better, right? So almost like a 20 percentage points improvement in the overall search results, right? So that's on fusion retrieval. Now, speaking of re-ranking, there's one really interesting technique, and probably a lot of you have already heard about this technique, but cross-encoder re-ranking is another technique where what you want to do is do a first pass retrieval, right? Where you use the by-encoder approach. By-encoder approach is basically where you are embedding the document separately, right? Like you're doing it as an offline process. You are compressing that to one single vector, right? So that's done as a pre-processing step, like we discussed earlier. And when your query comes in, you kind of do the same thing, like you pass it through the model, and now you have one single vector representation of that query as well. And then you basically just do a cosine similarity search, and you basically end up with a bunch of documents which are very similar to the query that has come in, right? However, the problem with this approach is that since we are taking like almost a page long or a paragraph long piece of information and embedding that and transforming that to one single vector representation, there's possibly there's some loss of semantic meaning, right? And so when we are doing the similarity search, it's probably not going to be as effective, right? And so the flip side to this is where you use a cross-encoder approach, right? So with a cross-encoder approach, you basically send the query as well as the document together to the model, right? Where it would basically just perform like a classification and identify if these two documents are similar or not. And that method allows you to preserve a lot of the good aspects of transformer, right? Like it has very semantically rich information to figure out with very high level of accuracy if this document is related to this other document, which is a query in our case, right? So assume document B is the query, right? Now, the problem with a cross-encoder is that it's very expensive to do, right? And the reason is, like I said, you have to pass the document and the query together to the transformer, right? And so it's like a early interaction model. And so that's super expensive to do. So when you're working with like a billion vectors, or sorry, a billion documents, this is just not going to be scalable, right? When a user query comes in, who's going to wait like half an hour for the answer to come up, right? So what do you do, right? So the one approach is to do a two-pass method where you use the by-encoder approach to come up with, say, 100 candidate documents, which are potentially the most similar to the query that we are trying to answer. And then you use the cross-encoder on top of these 100 documents, right? So you're only using a very small subset of the overall documents to perform a re-ranking using the cross-encoder approach. And now you have a much better approach, much better likelihood of finding the right documents, which right context, which can answer this question that we are trying to answer, right? So here's a block diagram that shows it. You have millions of documents here. You're performing, semantic or keyword search here. You fetch, 100 results as a first pass, and then you basically use the query and these 100 documents and perform a cross-encoder re-ranking. And now, you have this re-ranked result, out of which, again, maybe you take a subset, maybe you take the top 5 or top 10 and then pass it to the LLM. And now, your results are going to look much, much better, right? Now, that's great. But like I said, it's a very expensive thing to do, right? Like the cross-encoder re-ranker is quite expensive, right? So a third approach here is to use a Colbert approach, right? A Colbert approach is very interesting. What you do in this case is like a middle ground between the by-encoder and the cross-encoder, right? So in the by-encoder, there's no interaction between the query and the document. With a cross-encoder, there's like very heavy interaction between the query and the document, like we call it early interaction. With a Colbert approach, you kind of do a late interaction approach, right? What does that exactly mean? What it means is, in the Colbert approach, you try to preserve the token level embeddings, right? So what you do is you don't take the document and compress it to one single vector. Rather, what you do is you take, token level, you create token level embeddings, and you kind of retain it at the token level. And when a query comes in, you again, embed it at a token level. And then what you do is for every token in the query, you kind of figure out what are the semantically similar tokens across this entire corpus of tokens that you have, and you perform like a maxim operation, which is very efficient to do, very easy to do. Yeah, Stefan has just pinged a bunch of documents about using Colpally, which is Colbert on top of visual data, using Melvus. Thanks for that, Stefan. But just to quickly show you an example of this, right? So let's assume this is your query. Each of these are tokens. Like let's assume there are 3 tokens in your query, and you have these documents. And so what you're doing is you're trying to figure out for every token in the query, what's like the maxim, what is a maxim out of all these tokens. And so, you see that it's 9-7 in this case, 8-4 in this case, and 8-5 in this case. So you take a maxim, like basically aggregate that, right? So what this helps with is that you are still retaining a lot of that semantic richness that you have in your document, right? Like by keeping it at a token level, you're preserving that semantically rich information, but at the same time, this is a lot more efficient operation because you're doing just a maxim operation, which is very easy to do, very efficient to do. And so it's a great technique, and is showing some great results, right? The flip side though, actually I'll just come to the flip side really quickly. Here's a real example of the Colbert model where assume this is your question, and this is the document that you have. As you can see, like the transformer to transformer like match will be the highest because they're the same word. But then you have like cartoon matches with animated, the when matches with August and 1986, and the come out matches with released, right? So it's basically doing like token level matching, right, so to speak, right? And so that makes it like highly relevant and highly accurate in the context of a RAG, right? Now the flip side of this is that it takes a lot of search space, right? Because you're storing it at a token level. Storage can be really a big challenge. And so that's where Colbert V2 came into play. And so Colbert V2 uses a centroid-based approach where what you do is you essentially store like centroids, because you have the semantically rich information, which is at token level. You kind of can do clustering on top of those token level embeddings that you have, and create some centroids, and then basically do like a first pass match against those centroids to figure out like what tokens are the most closest to this, and then from the tokens you get to the documents, which results in a much better and efficient approach, right? So that's Colbert. I think we talked about a lot of different approaches and techniques, right? So let me pause here and let me ask you folks really quickly, how are you folks figuring out what is the right technique to use? For example, how do you figure out what is the right chunking approach to use? What is the right chunk size for the data set that you're working with? What technique are you using, or how are you figuring out what value to use, right? What chunk size to use, what chunking strategy to use, what kind of retrieval to use? Can you guys like type in the chat and share how are you figuring out the optimal setup for your RAG? Trial and error. Yeah. Not there yet. Okay. Got it. So trial and error is the most common and obvious way. I mean, there's really no other way, right? Like, how do you even know what chunking strategy or what chunk size is going to be better for you? I mean, at a high level, yeah, someone is mentioning here that you chunk based on relevance. I create separate documents based on departments or topic of the information. Cool. Yeah, but like there's no way to generalize, right? Like, hey, if you're working with financial documents, you use chunking approach XYZ. It's just not possible to do that kind of generalization, right? Because every data set is unique and there's just no one size fits all RAG, right? So creating an optimized RAG is actually really, really hard, right? And it just takes a lot of trial and error, which takes a lot of time and effort. And so, an example would be, let's say, you're working with, you're working on a specific RAG use case where you have to pick from 5 different chunking methods, 5 different chunk sizes, 5 different numbering models, and so on and so forth, right? Does anyone know how many RAG configurations this would produce, like in terms of the combinations? It's a math question. Let's see how many of you can guess. 5 raised to 7. That's right. Yeah. So this would create like 5 raised to 7, which is like 78,000 different RAG configurations, right? And if it took you just 5 minutes to try each one out, it would still take you like 271 days of nonstop trial and error, right? And so clearly it's kind of impractical to figure out the optimal RAG setup for your data set and your use case using a manual trial and error approach, right? This is why we ended up building RagBuilder. RagBuilder is a toolkit which performs hyperparameter optimization on the different moving parts of the RAG, right? So for example, it's going to figure out what's the right chunk size for your data set. It's going to try out a bunch of different chunking sizes, a bunch of different chunking strategies, and a bunch of different numbering models, and so on and so forth. And with every trial, it's going to figure out what's working, what's not working, and then kind of converge on the most optimal set of parameter values across each of these parameters, right? Additionally, it comes with like a bunch of predefined RAG templates. It also comes with the ability to do synthetic test data generation using Ragas. I don't know if all of you are familiar with Ragas, but Ragas is another open source library which is specifically focused on RAG evaluation. And so there's a synthetic test data generation. Yeah, we support knowledge base or graph RAG as well, and working on a couple of interesting roadmap items as well, like the ability to bring your own component and a cloud hosted option, etc. Right? It's completely open source, so do check it out. Maybe I can do a real quick demo so that you folks can get a feel of what it looks like. Awesome. Stefan is going to cover Ragas in an upcoming webinar. Fantastic. Cool. So installation is very straightforward. If you go to ragbuilder.io, there's this one-line command that you can copy paste, and you're good to go. It basically installs a couple of brew libraries and does pip install RagBuilder. Once you've installed RagBuilder, you just go to your terminal and type in RagBuilder, and it spins up a UVCon fast API app that runs locally, right? So it's going to bring up the browser in just a bit. Like I said, all of it is running locally. If you look at the IP address here, it's 127.2.2.1. It's running locally. So if you're concerned about data leaving your system or your platform, this is a pretty neat solution, right? Where you can, unless you're using a third-party AI service like OpenAI or Cohere, data will remain in your system, right? Now, let's say we're building a RAG, right? So I click on new project and I give it a description. So let's say I'm building a documentation chatbot. For a second, let's assume we are LangChain and we have a ton of documentation, and we want to make it easier for our developers to access this via an AI chatbot. And so let's create a documentation chatbot, right? Now, I've already scraped LangChain documentation, so there's hundreds of markdown files that I've put in this directory. But this field is pretty versatile. You can point it to a URL as well. You can point it to a directory, obviously, which can have like multiple files, or you can point it to a specific file as well, right? Now, if your data set is large, it will automatically scan it and tell you that, hey, your data set is kind of large. I've set the threshold here really low, so which is why even for a kind of like a 1 MB file, it's saying the data set is large. But if your data set is large, you want to start with sampling, right? So that you don't burn a lot of tokens and you get to iterate faster, right? So that's a pretty nifty thing. Like I said, we come with a bunch of predefined templates. So if I just show you this, with these templates, you can go from 0 to 1 really quickly, right? So if you want to create like a graph rag or like a hybrid rag, it's very easy to kind of do that. There's a bunch of templates out here, right? But where this tool really shines is the second option, where you can create like a custom rag configuration from the ground up, right? So let me show that to you real quick. So when we go next here, you can tailor the individual components at a more granular level in the screen. So for example, if you wanted to consider chunk sizes between 500 and 3000, you can just use the slider and it's going to figure out what is that optimal chunk size between this range, right? It's going to try out all of these different chunking approaches and figure out what's the optimal one. If you wanted to consider multiple embedding models, you can do that. Alternatively, if you have a very specific embedding model that you're working with, you can do that. We support Hugging Face. If your model is hosted on a cloud, you can do that. Yeah, let's select Milvus, right? Yeah, we support like a bunch of different vector databases, but obviously Milvus is pretty good. It supports like a bunch of retrievers. So we spoke about a bunch of different retrieval optimization approaches, right? For example, we spoke about the multi-query retriever, right? Like where it will break down the query into multiple versions of it, and query retrieve multiple documents based on multiple versions of the query, and then do a reciprocal rank fusion on that. So you can do all of those things, like you have BM25 retriever, vector similarity search. It's going to combine all of those, or try individually and figure out what is that optimal retriever setup. Obviously a top K parameter. And then within reranker also, like we just discussed, there are so many different techniques. There's your cross-encoder reranker, obviously, like Cohere and BG and so on and so forth, Gina and so on and so forth. But then there's also Colbert reranker, the one that we just talked about, and a bunch of other things, right? And then finally your LLM as well. So you can select the LLM of your choice if you want to use Grok, or if you want to use Ollama for a model that you're using locally, like a Llama 3.1 or 3.2, you can do that as well, right? Like I said, we do Bayesian optimization, so it's not going to do like a grid search or like a brute force search on all of these parameters. It's going to be intelligent, where it's going to start with a random set of values but figure out with each run what is working, what is not working. So how does it do that? It does that by using a RAG evaluation on the fly, right? Basically, you provide a data set, which is, think of it like a golden data set. I don't know if all of you are familiar with golden data set, but golden data set is just a term to say what's the set of question answer pairs that you can use to evaluate a RAG and figure out the accuracy of a RAG, right? So golden data set typically covers all different scenarios. It's basically comprehensive enough. So if you have that kind of a data set, you just bring in that data set and point it to the file which has that data set. If you don't have that data set, which is in majority of cases you don't have that lying around, like I said, we can generate that synthetically for you using your source data set, right? So in this case, like I had the LangChain documentation as the source data set, we can generate synthetic test data to kind of simulate what questions might users ask and what is the ground truth for those questions, right? So we can generate that synthetically.